Hello YouTube! Today we will be going over null spaces and ranges. Specifically in this video, we will be attempting to give a somewhat meaningful and natural motivation for the concept. So, asking a hopefully natural question, aka motivating the definitions of null t, null space, and range t, range. So, an essential property of a vector space is its dimension. So, what does a linear transformation t from v to w do to, well, the dimension of v? So let's set up our playing field. Here we have v, w, vector spaces, and some t linear. So t maps v to this thingy over here with the stripes. This set is the set of all images. So it has all the tvs in it. So due to t being a linear transformation, it preserves the vector structure of v, so this set over here is a subspace of w. Let's give this space a name. So, definition, vw vector spaces and t a linear transformation. We say that the range of t is, well, just a set of images. Now let's put on our thinking caps. Let the dimension of v be equal to n, so we're dealing with finite dimensional vector spaces as usual, and let b, well, the basis of v. So the number of vectors in B is the dimension of V. So let's see what t does to them. So we take our v's and we map them with t. Now, range t is v after being transformed by t. So range t is the result of applying our transformation t to v. So if we want to know what t does to the dimension of v, we want to know what the dimension of range t is. Thus we ask, is this list of vectors a basis of range t? So let's see if they span range t. Take any arbitrary tv from our range. By the definition of range, we know that there exists some v in our original space such that that v gets mapped to tv. Now, due to v being an element of our vector space v, and v being finite dimensional, we have that there exist these scalars over here such that we can express v as a linear combination of our basis vectors. Thus, when we apply t to this, we get the following expression. So, whatever tv I pick, I can write it as a linear combination of these vectors. The scalars are always there. So, the span of this list is indeed range t. Now, we have that these vectors span range t. Now we have to see whether they are linearly independent. So this list is either linearly independent or it is not. If they are linearly independent, then this list is a basis of range t, and we can conclude that the dimension of range t is equal to, well, n, which is also the dimension of v. Now, if they are linearly dependent, then we can remove the linearly dependent vectors and be left with this list over here. That is the basis of range t. Thus, the dimension of range t in this case is equal to m, which is strictly less than n. We have to remove at least one linearly dependent vector. So, which is strictly less than the dimension of v. Now, combining both cases, we get that, in general, the dimension of range t is less than or equal to then the dimension of v. So, conclusion, t can never increase the dimension of v. So, linear transformations always, they either preserve the dimension fully or they can end up reducing it. So, let's analyze the case when our t reduces the dimension of v. So what caused the reduction in the dimension of v? So if the dimension reduction happened in the linearly dependent case, so if these vectors are linearly dependent, then without loss of generality, at least one of them can be expressed as a linear combination of the others. So let's say that t of v1 can be expressed as a linear combination of all of these. So we do some manipulation, we get this is equal to this. Now, due to t being linear, we can do this, which means that there exists some v in v such that v is equal to this. So v is this linear combination, and v gets sent to the 0 vector by t. Now, due to the zero vector, the real zero vector, only having one valid unique representation as a linear combination of some basis vectors, in our case these vectors over here, this one the trivial one, we know that V is definitely not the zero vector. For example, we have here 1 is different from 0, so this is some linear combination and not all of the scalars are 0, so this V has no way of being 0. That we know for sure. So we can conclude that if these vectors are linearly dependent, then there exists at least one vector in V in our original space that is different from the 0 vector, such that it gets sent to the 0 vector in W. So that's valid, that's a thing, yes. And now here's a way to reinterpret that statement. So if T is some linear transformation such that it reduces that dimension of V, then this set over here, so of all the vectors in V that get mapped to 0, it is not equal to this set over here. So this set, if it's not equal to this, so if there are some non-zero vectors in this thingy, then for sure T might be reducing. Yeah, like it's a necessary condition. If T does the reduction of dimensions of V, then this thingy will definitely not be equal to just the space that only has the 0 vector. Something else will be in here. So this set seems kind of important. So let's give it a name. So V, W vector spaces, and T are linear transformation. We will call this set null T, which will be equal to all of the vectors in V that get mapped to 0. So yeah, hope that is enough to show how one might come up or stumble upon them, these concepts and definitions of null T and range. And yeah, in the next video, we will be actually proving stuff related to range T and null T. So hope you learned something. If you got some positive, negative feedback, feel free to leave it. Yeah. See you in the next one.